Oliver is a principal for cybersecurity at Siemens Corporate Technology. His current projects bring information security to the field level in IoT and OT. Oliver also represents Siemens in corresponding initiatives and standardization bodies, including PROFIBOS and PROFINET, INT's International, PROFINET International, the OPC Foundation, and the World Wide Web Consortium. Throughout his professional life, he was working in information security for distributed systems, so for IT, IoT, and OT, especially web-based applications. Oliver studied mathematics and computer science.
I want to talk with you about security for IoT as well as for OT, and that's from an industrial perspective. Since my employer is Siemens, industrial perspective usually will translate to Siemens. I'm also involved in a couple of activities in international consortia like other companies, but it's essentially a Siemens perspective. My name is Oliver Pfaff. I work at Siemens for a corporate department. I consult the business units within Siemens with respect to security, especially IoT and OT security. And in my case, that's mostly the digital industry business area or cluster within Siemens with which I work. And I want to give you a bit of the insights in the challenges with respect to IoT and OT security that we see here. OT is included for two reasons. One, it's not too distant from a demand perspective towards security from IoT. I will explain that in a minute. On the other hand, Siemens is a company which I think makes much more money as of now with OT operational technologies rather than IoT. IoT is, I think, a starting business within Siemens, whereas OT is a traditional business segment. Can you please go to the next slide? So I will look at three particular problems that come up in almost every project that I'm doing. Number one is protecting communications. To explain it simply, think about your preferred application protocol. If you think in the IT world, that might be HTTP. In an IoT world, it might be CoAP, or think about something else. So you have something like a preferred way of communicating within a system, and you want to protect it. against eavesdroppers, for instance, or components that manipulate. Managing security configuration and credentials, that's something you need to do in order to make the protected communications. So that's something that is a prerequisite, typically has to happen before. And identifying products also is something that plays into this game. That maps somehow, if you can click now to next, to the life cycle of an IoT OT component. On the left side, you see a life cycle chart, which is basically reflects something that is in an IETF-RFC document, which starts on the top with the manufacturing phase of an IoT or OT component. Then there's a bootstrapping phase. Then that's what you actually want to do. That's the operational phase where you use the product. Then there could be a maintenance phase where you update configuration or software, and then maybe there's an offboarding phase where you decommission the component and maybe sell it to somebody else. And when you look at that, then the number one, can you click, please, is of course the operational phase. It's our understanding the product in the operational phase. We would like to have security, which means we would like to protect communications for the whole operational phase, more or less. That requires us to do something before. I will explain that in some more detail. And before there's the bootstrapping phase. Can you click, please? So the managing security configuration credential here is shown in the bootstrapping phase. Of course, there can also be something in the maintenance phase which has to happen there. But right now, from the focus of getting it started, I just attributed it to the bootstrapping phase. And the identifying products topic, which is number 3, is something that relates to the manufacturing phase. Now we will go over these three things in a minute. Before doing that, I would like to give you a bit of my understanding of what IoT is and OT is. And so I think you are all very, very familiar with IoT. I understand it as something that is a system which has network components, where the components interact with physical resources in the real world, maybe as an actuator or maybe as a sensor. These components typically are computing devices which are created for a specific purpose. In IoT, they use the IP stack, possibly the internet, but at least the IP stack in my understanding. And the usages can be classified into industrial or consumer usages. OT actually has kind of the same characteristics as IoT. There is a plus. We often have highly time-sensitive use cases, especially in factory automation. And there's a large brownfield, which means there is a large heritage of both standards, products, solutions, installations, which evolved over the last 3 or 4 decades, which is just there and has to be respected somehow. There's a minus. Typically, I would say the IP stack is not there. It's not 100% true. If you look into PROFINET, they use RPC at some point, but there's an alternative like RSI. But anyhow, let's make it simple. We say there is typically no IP stack, and usually there is no consumer dimension. That's just industrial. When you compare it to IT, the big difference is that IT, in my understanding, does not really interact directly with physical resources in the real world. That's my basic understanding. If you can go to the next slide. You see 2 illustrations here. I think for IoT, I picked a home automation as an example that illustrates an IoT scenario in the consumer area. I gave some figures which are maybe somehow likely. I don't care too much here about the number of things in an IoT deployment. The important thing here probably, and we will see that in a moment, is that usually that's not a single manufacturer. So when you see at a single home automation facility, then you have a number of things, and typically you also have a number of thing manufacturers which is larger than one. Similar on the right-hand side, that's a picture from operations technology in the factory automation area, where you look into a factory. That's kind of a plant where the bodies of cars are manufactured. And you find numbers there which are higher, of course, by number of components. And you also find the same situation there, that in the real world, you don't find a single component manufacturer equipping one factory. So typically there is one factory and there are some 10 to 20 manufacturers, which means that all these things are kind of multi-vendor, multi-manufacturer deployments. In both cases, IoT and OT. So let's go to the next slide, please. Yeah, I already talked a bit of on my side. So I work for Siemens corporate development, which means I do consulting work within Siemens. I spent all my professional life in the, I have to be careful now, in the security area. Most of that I worked in IT security topics, especially here web and internet security for web applications or for internet-based applications. Also user management or so-called identity and access management topics. In the past, something like 6 years, I focus on IoT and OT. And here is especially the field level where I'm involved in. And one of the things here is the so-called PROFINET protocol, which is a field level protocol, which is used in automation systems, and where Siemens has a number of products where I help them with implementing security or specifying security for PROFINET. Right, so let's go now to the first topic. Protecting communication. So I introduced it. So think about your preferred way of communicating. Maybe CoAP, whatever you can come up with. And you want to protect it. Now let's first start at the bottom. In the IoT world, something that happened to be true in the OT world never was a real option. Something like physical security, in terms of you protect the components physically and run them in an isolated network. Even the terminology of Internet of Things already tells you that typically this is not the idea you have in IoT. So physical security never was a real candidate for protecting something. Also, the privilege here is the native ecosystem, which is the IP stack, and all the stuff around that already has cryptographic security, and that was established since the 80s. A lot of mechanisms there were invented in the 90s, of course, and they are used. Question is, should we reuse them? Or do we have to reinvent them in order to have good solutions for IoT security? Story is a little bit different on the OT side, because OT actually dates back to the days where the internet did not have any security at all, like the middle of the 80s. The security question within OT actually was answered by network segregation and isolation for many years. So there was no logical security in terms of protected communications or application of cryptography for the exchanges. That was simply unprotected. And every syntactically correct command was executed if you could send it to the target. And the protection was done by separating the network completely from the rest of the world. That worked for a number of years. It still works for a high volume of deployments. But nobody believes that this will work again for another 1 or 2 or 3 decades. So the OT area now faces a challenge where physical security is no more sufficient. And there has to be cryptographic security to facilitate new use cases, which could be something like vertical integration. You want to integrate your environment towards the cloud. I think you had talks about that, which is a valid use case, of course, which requires opening up, which then requires having additional safeguards and protections. Next challenge is the original ecosystem. When you look at the native protocol stacks, actually are unaware of cryptographic security. Some catched up here in the last years, and in the last 2 or 3 years something happened in some of the cases, but actually the original environments were unaware of that. And here the question is, how can we add cryptographic security? And now the important requirement comes without screwing up the genuine system. It's easy to add cryptographic security when we ignore the screwing up of something. So if we allow screwing up, adding security is simple. If we disallow screwing up, adding security becomes an art. And I will talk about that in a minute. So next slide, please. Here, I think we can be very quick. I guess you're familiar with that. Protecting communications actually is meant to deliver the usual functionality there. Of course, the often quoted requirement is data confidentiality. You want to pass data around, and you do not want to have a third party to eavesdrop and to interfere with the data. You do not want a third party to manipulate the data somehow or to replay the stuff. You do not want to have a third party to pretend to be another party, and you want to make sure that certain valuable resources, objects, or assets can only be accessed by the ones you would like them to access. So that's, I think, the very typical thing that we expect from protecting communications. Not too much special here, so we go to the next slide. And I'll start with the prior art. So actually, what is our tool set? And now the tool set is now including the IT perspective. And the tools that I display here on the left-hand side are not meant to be a complete list of the tools known on this planet. Of course, there are more tools. So I picked 5 prominent examples and placed them in the protocol stack. Let's start at the bottom. From the IEEE, there is a specification which allows you to protect the frame exchanges by cryptographic techniques between data nodes on data link, which is called MACsec, which is a layer 2 security technology. Then we have a layer 3 security technology, which is IPsec from the IETF. I guess that's well known. We have between the application and the transport, it's a bit hard to display that in an IETF-based stack. So I typically on layer 5 here, which doesn't formally exist, I guess, in the IETF, but anyhow, I need to put it somewhere. There's TLS and DTLS, which gives you security between client and server components in a generic way. And on an application object level, there's SMIME. Of course, as I said, there's many more. But let's work with the 5 here. There are some, can you click next, please? There are some commonalities. All of them deal with the kind of protection goals that we looked at in the slide before. Maybe we have to bring authorization or to set authorization here in parentheses, because typically that's a thing which is not fully covered, but which is enabled by them. They all use symmetric cryptographic schemes for protecting the actual application data, and use asymmetric cryptographic schemes for enabling key management for that. There's also some deltas. You can also see on the left-hand side, there's, of course, the placement in the protocol stack is different, as is shown on the left-hand side, which also means that the longevity of the protection that you can have is different. If you look at an SMIME protection kind of duration versus a MACsec protection duration, that's a different thing here. And of course, also because the protocol stack placement is different, the achievable end-to-end security span is much different between MACsec and TLS or SMIME, of course. Right, so that's kind of the chocolate box. Maybe we have more chocolates, but let's try to look at them and try to check what we could do with them. Next slide, please. So here I tried to kind of make an assessment on whether they are fit or not fit. In the assessment, you find the lines again of them, and then you find 2 columns. One is the IoT column and one is the OT column. You find green colors, you find red color, you find yellow color. The red color is the simplest, which typically means no, not really. You cannot really use that. And you have it 2 times in the OT column for SMIME and for IPsec. For IPsec, it's simple. You don't have an IP stack, so we would have a hard time using IPsec when there is no IP stack. And for SMIME, it's also simple. I never came across a store and forward communication pattern on the field level. In the IoT, actually, SMIME nowadays is translated because, or you have to see the ingredient of SMIME is something like CMS or PKCS7, which is cryptographic objects expressed in ASN1 language. That's the essence of SMIME. That's something which is recoined right now, or was recoined in the recent years. Security objects in the form factor of JSON and security objects in the form factor of CBOR. Here they are, I think, much more preferable. And collectively, the term is typically called object security, which means you objects, you apply the corresponding security stuff there. And then you have something equivalent to what SMIME does for the mail world, but it's actually not SMIME. So there's an affinity, but it's not SMIME for that reason. It's red. But of course, you find solutions in these classes there for IoT. The yes or the green blocks actually means they are candidates. They could become utilized to solve something. But it doesn't mean it's always a good solution. And depending on what you want to achieve, green doesn't necessarily mean you have to use it. For instance, here, if you want to have a rather fine-grained authorization model, you don't have much fun with MACsec because the authenticated information or the information that you get about the authenticated entity is pretty much coarse-grained. Maybe doesn't really relate to the endpoint that you would like to talk about. And so, yes, it's a valid technique. You can use it to control access to who is in the network, which components, but it's probably not the solution for your application level security task, even if it's green there. The complicated thing now is the DTLS discussion, and here especially with respect to OT. I spent quite a bit of my time to talk this topic here. And actually, I came up when I prepared the slides. The argument is too complex to have it here in that box. So I need, I think, 3 slides now to explain the yellow thing. Okay, so next slide, please. What we find when we look outside, we find 2 attitudes. We find one attitude that I call just use it as it is. So the IETF has a protocol which is called TLS or DTLS. There are a couple of versions. I don't care too much about the version number here. And you find examples of organizations as well as technologies which just use it. For instance, Modbus. There's a Modbus TCP security which uses TLS version 1.2 in the Modbus stack. The ODVA uses TLS version 1.2 as well as DTLS for the Common Industrial Protocol security. The OPC Foundation uses that for protecting UA communications JSON via HTTP over TLS. You find another attitude, don't use it. Just do your own protection protocol, security protocol from scratch. Interestingly, the OPC Foundation is a just user as well as a do-it-yourself party for OPC UI binary. They specify an own protocol, which is called UASC. UA stands for Unified Architecture. That's their baby. SC stands for Secure Communications. And that's a complete standalone security protocol, which does all the tricks that we had some 2 slides before, completely independent from TLS. Well, that's what we can find. Now let's assess it. Can we go to the next slide, please? Are these good ideas, or where are the obstacles? If you are looking into the just use it attitude and think about just using TLS or DTLS in an OT environment and ask yourself, is this a good question? Then I bring up 3 arguments here. One is the violations of determinisms. The OT environment, at least the areas where Siemens is having products, is heavily depending on determinisms. So the communications have to be heavily deterministic, and TLS has the habit of disturbing this. And the reason is quite simple. They use the same kind of transport for transporting protected application data, as well as protecting their own kind of security management data, handshaking data, which is a disturbance, of course, for the application, or a potential disturbance for the application exchange. And there are problems with things like bumpless key update, which is not really a problem in the IT environment. The user just waits a little longer for seeing the web page. That's not a problem. That can be a problem in a factory, saying you have to wait just a little longer to get the next instruction to a field device can lead to wreckage. There are alien objects, of course, because they have an encapsulation strategy, which means if you look into the network, you don't see your old objects again. There's also sequence number replay protection handling is pretty static. It's fit, of course, for the original purpose, but not necessarily fit for other purposes. Here also, since don't overinterpret this. This is, of course, not saying that TLS is not a good choice for HTTP. Of course, it's a good choice for HTTP. The argument here is just saying because TLS is a good idea for running it underneath HTTP, it's not necessarily a good idea for running it underneath any other protocol. We have to check this. When we look at the second dimension, don't use it and do it yourself, then you have following problems. TLS is quite rich, and there are quite some fancy features which you don't find at the first glance, which are important at the second glance, like something like trusted CA indication, where you can tell your communication partner according to which domain authentication should happen. This was introduced early in one direction in TLS, late in another direction. And it's easy, if you do your own protocol, to have white spots. It's also easy to create R&D costs. Because developing a good protocol is not cheap. And it's risky to have problems, of course, in the protocol. The literature is quite rich of failed protocol proposals from parties who believed, but who were not really able to champion the design of a security protocol. All right, so that's our not good alternatives. Can we go to the next slide? So what can we do if not using it is not a good idea, and using it is also not a good idea? To give an answer, it makes sense to have a little closer look at what is inside TLS and DTLS. There is a handshake layer and there's a record layer. The record layer is responsible, or the record layer is a client and server security protocol. So you have the record layer or the handshake layer on both sides. There's a client side, there's a server side. The record layer assumes that both sides already have a shared understanding of which keys and which algorithms to use, and just use them to protect data on the sender side and deprotect data on the receiver side. And the data that is protected and deprotected can be application data, which comes from the application that sits on top of TLS, or can be internal data which is owned to the TLS machine, which is handshake data. I'll explain handshake in a minute. So there's a record layer, and I explained the job of the record layer. The record layer, actually, the complexity part of that is, it's just, if you look at the number of pages in the specification, maybe the record layer has a 10% of the overall complexity. Because the actual complexity of the protocol lays in the handshake layer. The handshake layer has a different purpose. It's on the client side, on the server side. It's the negotiation phase. So you negotiate which security mechanisms to use. You establish the authentication of the communication partners in one or in both directions. You establish keys. And you negotiate, you have switching strategies as well as alerting strategies if something goes wrong. And the handshake layer is kind of an own protocol which runs over the record layer, which means if you look with Wireshark into the TLS records, the first byte in the TLS record header tells you if the payload inside the TLS record is actually application data, the gray stuff, or is handshake data the kind of brownish stuff here. which was the argument before with the multiplexing, which leads to determinism violations. And now the handshake layer actually is 80% of the specification complexity, maybe 90%. And when you look at the problems from an OT perspective, then the handshake layer has an 80% value share and just a 10% problem share, whereas the record layer has a 80% problem share. So the idea here is use TLS, not DTLS. Pick the handshake layer. Create your own record layer. That's pretty simple because the record layer in TLS nowadays is not much more than the usage of the so-called AEID algorithm. So if you have the AEID algorithm, creating an own fit-for-purpose record layer is a quite cheap exercise. Then typically, because there's no IP stack or no TCP/UDP, you have to think about what you do with TLS. You could wrap it into EIP, which is called the Extensible Authentication Protocol, another IETF standard, which allows you to run directly over layer 2, and also which allows you to embed other protocols than TLS. Kind of security sessions or associations, which you then use in C. And that's a recipe according which we cook the PROFINET security specification as of now. And that's the end of the protecting communications part. I'm not sure about questions. If there would be questions for this, maybe I'm happy to take them. Otherwise, we can also continue to the next part. Okay, let's go to the next part. So let's assume we talked a little bit about protecting the communications during the operational phase. That's what we want to do. The problem now is we have to prepare for that. There is no out-of-nothing security. You at least have to establish a shared understanding of the keys that you would like to use and a shared understanding of the algorithms. So you have to prepare something, and typically that has to happen in the bootstrapping phase. And this has to be done in an IoT, OT-friendly way. And that's one important thing we will talk in a minute. And of course, what you do there when you prepare for security, this has to be protected again. By the way, to give a side note here, that's one of the major obstacles that I face in my projects. Many people, especially non-security specialists I work with, tend to think that security comes and just solves things. The problem is security creates another security problem because with the cryptographic algorithms, you just trade the need or initially you need to protect some application data, maybe a message. And the cryptographic algorithms, no matter if it's symmetric or asymmetric, allow you to trade this into a key, but you need to protect the key. If you cannot protect the key, you cannot have control over the protected message, which means you actually trade the need to protect the message to the need to protect the key, which is something that not everybody intuitively understands, and which is a quite likely cause of some confusion in projects, because this is a dimension which often gets neglected by people who are not familiar with security. So we have to take care here. We have to make it secure, because otherwise it does not make much sense what we do on the application data. And we have to do this in an IoT OT friendly way. So actually this challenge here from a complexity perspective is much bigger than the protecting communication that we had at the beginning. So that's in my daily work, that's kind of the biggest challenge. And let's look at it. First of all, security configuration. There's the more boring stuff is which algorithms we want to use. The more exciting stuff is simple. When we have the means to protect communications, we have to distinguish between a state where a component accepts only protected communications, or it accepts plain and or protected communications. This has to be managed. There has to be an initial factory state. Then there has to happen something in the site. It depends a little bit if you have mixed environments where all the components, not all the components can talk security, then you have to have corresponding settings. But of course, if you allow plain communications, you can bypass security somehow. Well, that's kind of a compromise. If you want to have a high security, then you go for protected only communications, but this cannot be the factory default. Because you have multi-vendor environments and you have to manage the key. So that's it sounds simple, but that's a pretty complex security configuration management issue. The other problem is, of course, providing the credentials. Can click this? So like in TLS, the web server needs something at the beginning before the user can talk with the app or with the browser in a secure way. Same stuff here. Before we can protect the communications in a way where we want to authenticate mutually between the components, we need to have objects for doing that. And they must be provided. And this supply must happen in the bootstrapping phase. It cannot happen in the manufacturing phase, because in the manufacturing phase, the component does not know anything about the local name. So let's look at an example. When you look at the OPC UA specification, they use things like application URI, DNS, or IP address, which is information which is created during the bootstrapping phase. It's not available in the manufacturing phase. And you have to have such objects with such information. You cannot produce these objects in the manufacturing phase, at least not in product business. You may do this in solution business, but that's a different business type. The business units I work with in Siemens are all product business units, which means they ship generic products which don't have any particular knowledge about the deployment in which they want to run. Which means the information that we have to supply here must come to the component in the bootstrapping phase so that we can use it in the operation phase. Let's go next slide, please. I said before, same problem in web and all the other usages of TLS or other security protocols. And how do they do this? So usually you see the gray box is something like a host computer. So think about a, I don't know, Linux system. Then there's an application component down. Think about a web server and Apache HTTP, and think about normal users trying to access. And you want to protect the communications the normal users are doing. This happens via TLS. Typically, there will be server authentication, which means you need to have some configuration. You need to tell the HTTP server to kind of run in a TLS mode. And you need to coin and to supply the server certificate object together with the private key and so on. This has to happen, and the application component is the user of such information. How the management is done is not too well known to the normal user because there is something like a privileged user. And the privileged user has the role of doing this using an administration component, for instance, system console, and the privileged user is managing that. There are some examples. I picked Apache Tomcat here for an example. So you manage the server XML. The server XML refers to some credential objects, which could be PKCS12 files, P12 files on the file system. And you use either the local file system or some dedicated hardware for storing and using these credentials. And that's a common approach. Can you click, please? So the commonalities are use a second communication channel for managing the configuration and the credentials. And this is done by a dedicated user, which is called the privileged user here, and that's different from the normal user which uses it. Of course, you can imagine there are many form factors of implementing it. So that could be the privileged user could, for instance, be use a keyboard and a local screen and the operating system and the operating system users, or it could be remote via secure shell and so on and so forth. It could be an interactive privileged user. It could be a scripted thing that happens there. So there are many ways of playing the game, but at the end of the day, it looks like that. Okay, next slide, please. Now, first question, will copy and paste work? Here, clear question, no, at least not in general. Maybe in special cases it can work, but not in general. The IoT-OT components, especially the ones that we encounter within Siemens, do just not have the means that are the backbone of the IT security solution. So there is no keyboard, there is no screen, there is no system console, there is no operating, no user knowledge or no perception of a user on an operating system. There are no operating system checks. All these things you are used to from a Windows environment or from a Linux environment are just not there. And maybe that's different here for a controller, which is a component in OT which controls field devices, but at least it holds for the field devices, which are the components that really interact with the physical world. So they're just not there. And so the question is, how do we implement the privileged usage which manages the security credential and the configuration? And here the trick is quite simple. Like many problems in computer science, the current idea is we add another level of interaction to solve the problem. So we introduce another set of credentials, which, and we say we have two credential sets. One is the credential set A, which we use for protecting the normal communications. And then we assume we have a credential set B, which we use to protect the privileged usage. That logically or from a model perspective works fine. Of course, it creates the problem. How do we protect the management of security configuration in credential set B? You can iterate that a couple of times. Then you can introduce C, D, E, F, but at some point in time you will be bored and you will stop. Then you have actually two options at the point where you want to stop. One option which is attractive from a security perspective, but not ubiquitously available, is if the manufacturer provided some original credentials during the product manufacturing, then that's something you could use to protect the initial set B or C, whatever you use there, and the management. If it's not there, you have to do this in plain form in a physically protected environment with contextual protections on the local side. Okay, next slide, please. Question, of course, because it's different than in IT and it's counterintuitive, and it really costs quite some oxygen to have discussions on that with non-security experts. So we always have to answer the question, what are the alternatives? There are not too many alternatives here. You could think about, we did just disable the management feature for the credential objects and the configuration while we are in operation. That's thinkable, but then you have the problem, then you have something like eternal keys that you frequently use in authentication processes, but that you cannot really update anymore, which is a bad practice. When you say no, I don't really care about protecting the credentials that I use for protecting the applications, then actually it doesn't make much sense, because the persons who would like to penetrate your system then penetrate you at the point where they inject their credentials, they establish authority of the credentials and keys, and under that they can penetrate you on the application exchange level. Protecting with the same object doesn't really work, because you cannot protect the initial supply. The object that you would like to use, I call it A, the set of objects that you would like to use for the application exchange, cannot really be used for protecting its own establishment, because it's just not there at the point where you would like to use it. Cloning the IT receipt could work, but would be very costly and would screw up the genuine systems. We have seen the slide before. Good way of thinking when we look into security enabling PROFINET, and that's the pattern according which we are specifying the solution for that. Because there are not many good alternatives, as I tried to show here. Well, I think that's the end of the second part. And now the third and last part comes with identifying products. The products in IoT and OT typically already have product identifiers, and they are locally unique. I gave you examples for Siemens products. So you see on the right-hand side, you see an area of Siemens products. They are controllers which control field devices, and they have on the body of the component, they have badges, and a part of the badges, you have something like product serial number. There's a number of information. There's a product serial number, and the product serial number is shown in. And they are just locally. They're locally unique. They're locally among Siemens product components. They are not locally. They are not unique among the set of controller components that can talk PROFINET. And the question is, how can we move to something more? Olaf, next slide, please. Yeah. Before I have to motivate them more. The point is, what is the use case for having more than locally unique? And here, the use case is verification of machine originality. And the use case, you build a machine, like an industrial robot that I showed here. It was again at the slide number 3, I think, at the beginning, where there was an industrial robot, and that's comprised of a number of OT or IoT components which come together and build a machine. And let's assume the customer would like to make sure that the machine that he gets actually is from the, has all the components and all the equipment that he's thinking he buys. And he wants to verify the originality of the machine, which typically requires the machine builder to make assertions about the components. He has to talk about the components that are part of the machine. And that's difficult if we only have locally unique identifiers, because then the machine builder has to make them kind of more unique than locally unique, which means the machine builder would have to introduce some namespace stuff. That could be done, but it's awkward. And it would be much simpler if the machine builders would do that. Next slide, please. There's prior art. For instance, from automotive, there are vehicle identification numbers which are globally unique among the motor vehicles on this planet. In banking, there's the International Security Identification Number, which is a unique number about the securities that can be traded at exchanges. And in media, there's the ISBN, which is a unique number for books. Next, please. They are globally unique. Typically, they have an ISO scheme. They are to enforce them. There are dedicated accreditation and value authorities. There's also deltas, for instance, the scoping of the identifiers. In the vehicle identification space, it's really the instance of a vehicle, a specific car. In the media or book area, it's a variation or an addition of a book, not the printed instance. And also the value authorities can be different. In the vehicle identification number space, it's the vehicle manufacturer, the automotive company. In the ESIN space, it's a national authority. Next slide, please. Here again, question: could we do this by copy paste? In theory, yes. But in practice, no. We have to see that the stuff was invented in the 80s, more or less, and it's quite limited in structure and expressibility there. And also the establishment of the overarching structure is very complex and takes time, takes lots of oxygen to establish that. We have a privilege that we have new building blocks right now. For instance, there are things like URIs, and there's also things like registration authorities for the internet, like ECAN and IANA, that can be used for doing it. So it looks like we have to do the same thing, moving from local unique to global unique identifiers for IoT and OT products, but we probably can make use of new techniques. Next slide, please. How could that look like? Simple receipt here. URIs could be candidates. I give 3 examples here. That's a classical URL scheme first, and that's a URN scheme, which are classical options. There are new options like DID, decentralized identifiers, which are currently in W3C elaboration work. You, of course, need to establish an ownership and governance for the most significant URI part, which is the authority in the URL case, the namespace identifier in the URN case, and the method name in the DID case. There are a couple of candidates who can play the role. The authority, for instance, is an econ managed thing. The namespace identifier is in IANA. It's a preliminary managed thing by the W3C. Then you have this syntax, and you can reflect organization structure, product portfolio, and you can especially include the already existing values somehow, and can build value-added use cases on that basis. Right, next slide, please. So that's the conclusion now. And so let's look over the things. So first of all, the topics that we discussed have significant relevance in my R&D work. So the last 2, 3, 4 years, almost all of my time was somehow devoted to one of the 3 topics, 1, 2, or 3. For some of them, not any of them are fully finished. So work is still ongoing, especially also the protection thing, which is pretty much straightforward, actually appears again and again and again. Number 2 is quite complex. Number 3 is just starting right now. So in that case, I would not say that any of the work is finally done and nothing else has to be done in the next years. I rather would guess that work in these areas will last for another couple of years, maybe 1 decade. Next, please. Here, I would like to point out, for protecting communications, IoT and OT as well as IT actually share the same problem, but the sharing of the solution is partial. In some areas, the solution sharing, there may be a solution sharing, and the solution sharing could be large. In other areas, the solution sharing is little to none. And the affinity of a given IoT OT ecosystem to IT will tell you if you have a large solution, can have a large solution share, then you should exploit this, of course. Or if you have a little solution share, then you should be more careful and not use copy paste. Next, please. Managing security configuration. As already said, IoT and OT as well as IT share the same problem. It's common, but here I would say they don't share the same solution. The solution that we see in IT cannot be the general solution in OT. Maybe it can be a solution for some things in the IoT space, but not for everything that I'm aware of. So we need new solution approaches here. Next slide, please. Here, next, click this, sorry. Identifying products, IoT and OT do actually not share the same problem. So product identification really has to do, at least in my understanding, with the physics of the product, which is typically in the IT thing is different. So I would rather say they don't even share the same problem. You find additional challenges. There's an interesting RFC on the IoT security state of the art, which I quote there, which has a number of additional challenges that are all relevant and interesting, and I recommend to have a look at that. Thanks a lot.
This time, as is the last presentation, this time we'll apply the mode that you can ask your questions yourself. Nicolas will call you, and then afterwards you can raise your question. But let me start with the first question. It's a double question, so it has two aspects. So the first one is, why, Oliver, do you think that especially in this security field, people are always trying to reinvent the wheel? So why are they like, oh yeah, there's a security solution, but we don't want to go for it, instead of doing what you did, namely analyzing, okay, what is fitting, what is not fitting from this solution, what could we adopt from a standard that is there, from something that is well established, a de facto standard. Instead, I have the impression that they often go for, okay, let's do greenfield approach because we know better how to do security. And the second question related to that, how could we incentivize the people to rather do what you so greatly showed us in your presentation than saying like, oh yeah, nobody did security well, so I will do it from scratch. You have to unmute.
Right, thank you. Yeah, for the first question, the attitude that I often find actually is rather to reuse the wheel. So typically in the discussions that I'm involved in, there's an attitude, let's make a copy paste from the stuff that we know in IT. Which actually from a reuse perspective is okay. So typically it's also my understanding in we create value by reusing things which were already there, which is a good idea if it fits. I often have to fight, or I often have to bring up the question, does it really fit? And then on the other hand, yeah, in some cases, it's reinventing the wheel, and both are going beyond the where they actually should go. When I find camps that do reinvent, that typically means they don't fully, at least in the cases that I encountered, they don't have a full understanding of the available mechanisms. So even TLS, it used to be a tiny 30, 40 page document in the 90s. It became bigger. Actually, to be fully up to date with what the IETF is saying on TLS is kind of a full day job, more or less. If you want to read all the RFCs and the drafts and all the conversations in the group. And my understanding sometimes is they don't really invest the time in understanding what's there, and just kind of it's simpler if we ignore what's there and just read the thing. So yes, I think there are issues in both directions. So yeah, overestimating, so copy paste can be found quite often. Not reuse anything can be found quite often. What's the best way of getting ahead? I'm confronted with this phenomenon since a couple of years, and I don't yet have a good answer for this question, I believe. So I do it on a basis of kind of daily work. For instance, in the PROFINET environment, I really had to go into the working groups and had to work with the people there for a period of 3 or 4 months to establish the mindset that I think could have been there before.
Mm-hmm. And I deeply admire you for this job, because it's a super interesting job, and it's at the same time a super important job, because what I always tell the people is like, without security, nothing. So things cannot fly, because it's really the basis, even though you think that it's not so important until something crashes. Okay, good. So I hand over to Nicolas for calling these speakers.
Yes.
I think you will be your voice as well.
Okay, can you hear me?
Yes.
Yes. Mm-hmm. Okay. So Oliver, I don't know if you saw it, but in the Zoom interface, you can open the chat window.
Yeah.
So you can see a bit the question, but I will ask the students to ask the question as well, so we can all hear it. But at the same time, you can read them as well, so it's easier for you to understand the question and to answer it. So I will start with you to open your mic and ask your question on your consumer and system interaction.
Yes, thank you very much. Am I audible?
Yes.
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 Okay, thank you for this nice presentation that you gave. So I would like to ask you that with the introduction of consumer-centric devices, for instance, if we take an example of smart meters, where consumers can access the device and they can operate it manually. So what are the challenges with the existing communication mechanisms that the company faced? From the consumer end, because there is more possibility of accessibility, more chances of attackers intruding into the system. What is your perception and how the company deals with these scenarios? Thank you.
Yeah, actually, that's probably a hard one for me to answer, because Siemens is not doing many business in the consumer area. So we are more facing in the IoT environment. That's more facing the industrial space, and the OT thing actually I think is purely also kind of commercial or industrial. Let me try to answer it from a more generic perspective. I think if you think from it from a device perspective, I think the first question would be what actually is the kind of network reachability. So do you design it, or is the device you're thinking about, do you imagine it as just accessible in the local network, or do we want to have it accessible via the internet? Local network could be something like Bluetooth or wireless LAN, which requires you to be at home, for instance, to do something. Of course, then you cannot have on a business trip, for instance. So these are kind of two important things. If it's local, you need to safeguard kind of the network, and you need to make sure that how to say, usability is a key point here. Because the user then has to do all by itself. If you have an architecture where you have a middle component where the user actually calls an infrastructure that you control, and your infrastructure calls the component, then you may have it a little more simple, because actually then you just have a kind of a normal web security scenario between the application and your application, and then down to the component. So maybe question back, which of the two scenarios were you thinking of?
It's like when the network is open to the users, where they can directly interact with the network through the device.
Yes, and you would assume the device is accessible from any point. So you have internet connectivity anywhere on the planet, and you would like to access the device, or can we assume that has to be a local network?
It's through the internet connectivity. Okay,
through the internet connectivity, then I think the architectural model is yeah. I'm hesitating a little bit to say straightforward. Maybe it's not too straightforward, but you have two legs here in the communication. There's one leg between kind of the application component, which runs on mobile, and then maybe a computing infrastructure that could run in the cloud or somewhere, and then something that runs to the device. An example would be that I was involved a bit is something like the car connect infrastructure in automotive. And then you typically have kind of a normal web security scenario between the application and the app or the browser. as well as the application that you supply there. But you have many applications, so you could have requirements on kind of usability scenarios or single sign-on there, and then you have to make sure that the communication works there. In the automotive, they have an interesting approach there. Because they actually use something, they also hide things a little bit there. They use secondary communication channels via SMS messages, which are sent to the car, which actually implements a client that then calls the infrastructure. So that's possible. You can also revert it. Typically, I think you would want to come up with a design where the user doesn't have to do too much with the component. So typically, I think here the trick is to come up with a design where the user just sets up the component in the home, presses power on, and then things should work automatically, which of course then creates all the questions that I tried to talk. How do you protect the communications? That's typically a more simple thing to answer. And how do you manage the credentials? So I'm sorry, maybe I don't have a direct answer. It really depends a little bit on the details. What is the protocol? What are the mechanisms? What is the usability? What is the value? How much security do you want to have? How much user interaction can you require? So I think there's no one-size-fits-all solution.
Okay, and that's quite informative, sir, from your side. So thank you very much for your answer.
Yes, thank you. So we go to the next one, and I would like to ask Anuragini to open the mic about the product identifier. Anuragini, are you still with us? Maybe not. So I can read the question anyway.
Yeah.
Okay. So the question was about the lack of project identifier and the lack of standardization, and how can this impact the cybersecurity certification that is supposed to happen at the EU level?
First point, I think there are product identifiers. I would not say there are no product identifiers. There are product identifiers that are common. Even in the consumer space, the product I came across typically had them, but they were all kind of locally unique. So they were good enough if I have to get back to the manufacturer and have warranty claims, for instance. And if I have to report back which product I got and give the number, so things like that can be I think sufficiently managed. And the use case that we are seeing here is really from a machine building scenario, which I think is deeply in the industrial space. I'm not involved with the details of the EU regulation, but I would assume that it's more high level. So right now, I cannot really imagine that the kind of challenges that I was trying to bring up are somehow directly related to something that the EU wants to regulate somewhere.
Okay, thank you. Then we have Philippe with a question on TLS, but maybe before Philippe asking the question, I wanted to ask you, because in the first part, you removed DTLS and you chose TLS for Internet of Things, if I'm not mistaken. And I was wondering why, because a lot of applications are running on a UDP based instead of TCP based for the IoT.
Yes, it was here more focused, I think, on the OT scenario. We have to worry about running a security protocol in an environment where we don't have a TCP/IP stack, or where we say we are kind of largely in a kind of a UDP scenario. For us, it is more appropriate to do this by adding EAP than picking DTLS. Because we have a couple of advantages here. When we pick EAP and wrap TLS into EAP, there are a number of advantages. Number one, EAP is an umbrella around authentication protocols. So, which means underneath this umbrella, you can have others than TLS and maybe even future protocols. And you can also have additions or combinations of authentication protocols. That's an inherent example. The other thing is in the PROFINET environment, we have to again wrap the objects into PROFINET objects. And if you use, now I don't care if we talk TLS or DTLS, if we would use one of the two, TLS or DTLS, and would wrap the handshake messages, we would have to do the wrapping some, I don't know, 12 or 15 times, because we have 10 or 12 objects. And if they change the specification, we would have to redo it again. And I think in TLS version 1.3, they introduced new types of handshake messages. So we would steadily have to wrap stuff. When we add EAP around TLS, we have a very simple request response message pattern. And so the next layer of wrapping gets much more simple. We just have to worry about embedding TLS request response into PROFINET messages. And then the rest of the job is something that somebody else has to do. And when you combine that, then we have more advantages by inheriting our security protocol from TLS handshake plus EIP than using DTLS handshake.
I see.
So it's more a tactical thing. At the end, from a feature and use case perspective, you get the same.
Okay.
But it's less work and you have more potential.
Much. Philip, do you want to continue with your question on TLS?
Yeah, sure, thanks. So I already, because I was assigned to the same room with Oliver during the breakout session, so I had a chance to discuss, but I think it's also interesting for the others. So my questions was regarding the choice of TLS 1.2, and namely which cyber suits and which key exchange algorithms are preferred or recommended in the domain of IoT, and which are currently dominant. Yeah, thank you.
Yeah, to comment quickly on that again, so the OT specifications that I'm actively working on, they also have a version history. And so we talk now about the first version. For the first version, it's not finalized right now, so I will use the word likely. It's likely that the TLS protocol version will be 1.2, not 1.3. 1.3 is an RFC right now, but code coverage as well as depth of understanding of TLS 1.3 still is inferior to 1.2. By the way, when you double check, I think they should have called it 2.0. There are even, I really follow TLS since the mid of the 90s. And from 1.1 to 1.2, from 1.1 to 1.2, the steps were kind of minor. And now from 1.2 to 1.3, really, it feels like a new protocol. And I think the better term would have been TLS 2.0. And for that reason, I could see an adoption in the later phase, but for first version of what we are doing, I think it will be version 1.2. On the Cypher Suite side, I think we will there will be an offering of something like 3 to 5 symmetric algorithms, and it's a pretty safe bet that we will see AES in Galva mode, GZM with 128, 256 bit as 2 items on the 3, 4, or 5 item list. On the side of the cryptographic algorithms, the discussions are ongoing right now, but there is, I think, a preference for elliptic curves. The argument is not so much the computation time and the computation performance. Interestingly, is the size of the certificate objects gets smaller, which is something that has to be stored, and that's a new object which hasn't been there now, and the amount of storage which is available in a persistent way over power on, power off is quite limited, and then that kind of drives the discussion towards elliptic curve.
Great, thank you.
Thank you very much. And we have a last question, Nicolas, still about a TLS and comparison with something else.
Okay. Hello. So my question is, can you quickly define the differences and the advantages or disadvantages of your TLS approach compared to the OPC UA security communication protocol?
The argument that I see here is the following, and I try to indicate this with the trusted CA indication. If you remember in the part 2, I tried to explain that we have to deal with sets of credentials. I think I called it A and B. So there's a credential set, I think it was called credential set A, which is used to protect application communications, and then we need the credential set B to protect the management operations for credentials. And maybe there's a set C, which tells you that we have to have mechanisms to tell the communication partners, is this game now played with belonging to A, B, or C? That's a mechanism we need. And when you search for this mechanism in a protocol like TLS, you come up with things like the trusted CA indication. That's a mechanism. It wasn't called trusted CA indication, but from the first day of TLS, the server could ask the client for client authentication, and in asking, you could indicate which authorities you would accept. And with a later extension, which is available in TLS 1.2, the client can also tell towards the server what it is expecting, which helps multi-home scenarios for web servers, so that the web server can actually present a web server certificate which kind of matches the expectation. That's a mechanism which is there and which is not there in UAC, which means that this protocol, you will have a hard time, I believe, to make this protocol something that you can easily use in a bootstrap scenario.
Okay.
That's one example. I think one could come up with more. So I think they kind of they wanted to shorten a 30-page specification to 3 or 4 pages, and of course there is a loss. Up to now, they didn't feel the loss for their use cases. I think they made a transformation which is fit for their use cases. But when new use cases come up, there's a chance that among the 35 pages that you cut it away, there could have been something that you need now. And I try to give you an example for that. So I think they made a shortcut, probably for good arguments, but if you mature and have new use cases, they would have to touch the protocol again, I believe.
Okay, thank you.
Okay, great, wonderful. So we had lots of discussions, very good. So we really managed to stimulate the audience. Thank you very much for that.
Thank you.